So in this video, what we're going to do is talk a little bit about the sources of magnetic field, which are moving charges. So what we observe is that if there's a positive charge somewhere and it is stuck, we will observe an electric field that charge produces. And we can calculate that. We can determine how big it is. We can determine the interactions between the electric field that charge produces and other charges. But a new idea is if we actually allow that charge to be set into motion, so it starts to move. So if that charge is moving with some velocity v, then that charge is observed to produce a magnetic field that has to do with how much charge we have and what speed and in which direction it's going. The mathematical model that's associated with this situation involves a cross product. So we will write that all down. This magnetic field associated with a single moving charge is equal to mu naught over 4 pi, which is a new constant. The charge itself, v cross r hat over r squared, where this r business is essentially the separation vector that we've seen before that points from the source to the observation location. So if we have some origin of coordinates, let's say like here, so that's where 0, 0, 0 is, there is a vector that points to the source, and there's a vector that points to the observation location. And just like we had before, the separation vector is the difference between the observation location and the source, just like with the electric field. Now, let's unpack the different parts of this guy here. So first off, the constant mu naught over 4 pi is just a new constant. It's equal to 1 times 10 to the minus 7. Q is the charge, which includes the sign. V is the velocity of that charge. So not only how fast it's going, but in which direction it's moving. And R, as we said, is this separation vector between the observation and the source. And as a reminder, r squared is just the magnitude of r squared, and r hat is equal to the vector itself divided by its magnitude, as we've had before. Now, what's interesting about this is that there's a cross product here that's associated with the direction in which the charge is moving and where you're actually doing the observation. And so the magnetic field points in the direction of that cross product up to a sign, and that sign is determined by the charge itself. So what we have to do is get a sense of how that works so that we can determine the direction of the magnetic field before we do any sort of calculations. So let's take, for example, I have a charge that is moving with a velocity v. I'm going to take it to be a positive charge. And I'm going to say that I'm interested in the location over here. So this is point P that we are interested in finding the magnetic field at. And so what we have to do is dust off our cross product, right, our right-hand rule. So we take our right hand, point our fingers in the direction of the velocity, that's the first vector, and we rotate through the smallest angle to the second vector, which in this case is the r vector, which also points in the same direction as r hat. And our thumb tells us the direction that the magnetic field will point up to a sign. This has a positive sign, so we maintain the direction. And so the magnetic field, in this case, points out of the page, or out of the board. If this charge were negative, we would do the same cross product, v cross r, but we get an overall minus sign from the sign of the charge. So we flip our hand over, and it turns out the magnetic field will point into the board. Now, that makes sense, right? A positive charge moving in the exact same way as a negative charge should produce a magnetic field that points in a slightly different direction. It turns out it points in exactly the opposite direction. That's exactly what you saw with electric fields. What's different about it is that the plane that the velocity vector and the separation vector define, which would be the plane of this board, the magnetic field is perpendicular to that plane. That's exactly what a cross product does. It produces a vector that is perpendicular to both of the vectors that construct it. So the way that we actually think about this and the way that we diagram it is maybe a little bit new for some folks. So if you think about an arrow like this, if you think about something that is pointing out of the page, you think about the arrow pointing towards you. And so you would see the tip of the arrow. And we represent that as a circle with a dot. That is, you're seeing the tip of the arrow. On the other hand, if you're looking at a magnetic field or something that points into the board, what you're looking at is an arrow that points into the board. So you're going to see the feathers, which would be into the page. And so we represent that with a cross, right? The idea that you sort of see the arrows, the feathers crossed when looking at the back end of the arrow. So this description here of the magnetic field in terms of a cross product tells us a little bit about its direction. We can also exactly calculate it, which is done in the notes for a particular choice of charge and location. But another thing to sort of keep track of is this representation of pointing out of the page or pointing into the page to be able to determine the direction of the magnetic field.